step, 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 to the end. Now, I don't have to do that. I can initialize it and run it like that. But this is pretty boring. I can ask, what happens if I change the value of r? So I don't want this to just be one value. I want to run it many times with different values of r. So I've got to have a way of doing that. So I get what is called a slider. Here's a slider. And I'll call this slider r, okay? And I want the slider to go from 0, let's say, to 2, and up to 1 decimal place. So it's going to allow me to choose all values of r from 0 to 2, like a 0, 0.1, 0.2, and so on. And now, instead of r being a specified value, I'm going to make it the value that's at the slider, okay? And here the slider's at 1, and I can go capture, load, exec. Nothing happened. Why did nothing happen? R equals 1, so I kept getting the same value that I started out at. If I make r bigger than 1, and I execute it, that happens. If I make r smaller than 1, and I execute, and that happens. But now, what I can do is I can put it in auto mode. And instead of getting a new graph each time, I can compare what I get. And so I'll get capture, load, and I'll execute it. And now I'll change the value of r. Oh, I put it in auto mode. Okay, so exec. And I'll change the value of r. And you can see that you get different runs, and each time you change the value of r, you get a different value. Okay, so this allows you to just play around with your models. You can grab your slider here. You can put it in auto mode or not, and you can play around with it. So if you have a look at your work set, I probably got rid of it, but it's going to be here. You'll see that the first thing is to build this model and to start out at x equals 100 and to play around with different values of r on the same graph. What do you conclude about the value of r with regard to being less than or greater than 1? And you've already seen, you know the answer to that. Okay, so the next one is to build a differential equation model. Now let's go back to the lectures and just talk a little bit about models that involve derivatives instead of sequences. Okay, so we've looked at that, and we've talked about sequences. Now, if you remember, this expression, what does it mean? So we have n as a function of time, and we can plot n versus t. Now, most of your calculus class, you probably use y and x. But when we're building models that, say, involve populations, we often use n and t, or x and t, or something. So don't get confused. So sometimes I might call this axis x and this axis t, or I might call this axis y and this axis x. So x does not mean the x-axis. Never say the x-axis. Say the horizontal and vertical axes. And sometimes the horizontal axis will be t, sometimes it will be x, sometimes the vertical axis will be x. What you won't get is x and x, which is not entirely true. You might get n at t plus 1 and plot it against n at t. So these variables, but they've got to have different names. Okay. So in calculus, this is some kind of function. So if I say, what is the n dt? So the n dt has a definition. And if you read your textbook, it'll tell you that a derivative is sometimes also a function. And the n dt can be a function of t itself. So here we're actually looking at a function f of x in these notes over here. This derivative is defined in terms of f being a function of x. So what does it mean to say df dx if f is a function of x? It means we're looking at the limit as h tends to 0 of f of x plus h minus f of x all over h. Now, in some textbooks, and I'm going to change the notation here, I'm not going to call this h, I'm going to call this delta x, a small change in x. And so wherever h, I'm going to call it delta x. So it's exactly the same thing. I can either call it h, I can either call it delta x. So I don't know which definitions you saw. It's all the same thing. It's just what you call these derivatives, these small changes. So the miracle of calculus is to say that this limit exists and means something. Now, unfortunately, in a digital machine, you can't allow numbers to get infinitely small, just like you can't allow numbers to get infinitely big. They're called finite machines because they can't deal with infinitely small things or infinitely large things. So what we do is we numerically simulate or numerically estimate things by saying df dx is approximately f of x plus delta x minus f of x over delta x for delta x very small. And the smaller delta x is, the better this approximation is. So when we talk about numerically simulating things, we're choosing a thing called delta. And this thing called delta that we choose is that because in the computer, we calculate the value of the function at x plus delta x minus f of x divided by delta x, but we can't allow delta x to go to 0 in the machine. But if we make it small enough, then our solution is approximately good, or approximately correct. And what I mean by that is that it's going to be correct to a certain number of decimal points. Now, you can't say ahead of time how many decimal points it's going to be correct to. You have to check that. So you can see that when you do a run of the model and you choose delta equal to a certain size, like 0.1, you can rerun the simulation and you can choose delta equal to half the size, like 0.05. And you can say, when I do that, the answer I get changes in the 4th decimal place. Now, if you only want the answer correct to 3 decimal places, then you're done. So that's what it means. And this approximation here is called an Euler approximation. E-U-L-E-R, famous mathematician, one of the greatest mathematicians, and the one that E is named after, Euler approximation. But you're also going to see that it's something called Runge-Kutta, abbreviated as RK, and there'll be an RK2 and an RK4. What this does is, instead of approximating this derivative by something as simple as that. It's a more sophisticated approximation, so it's more accurate. And that's all you have to know. If you're really interested, you can go to Wikipedia and look at Runge-Kutta methods, and you'll see more than you possibly want to see, unless you're a nerd. How many people here are nerds? Okay, great. I'm one too, so that's good. Okay, so now what I'm going to do is I'm going to build a model of where we say, okay, imagine a model where dn dt is some function of n. And in the simplest case, I'm going to say this is equal to r times n. And I'm going to actually make it a little more complicated. I'm going to say it's r times n to the p. And why do I want to do that? Well, here's something rather interesting. I swear I had something interesting to show you here. Okay, it's in the textbook further on. We'll come to that in a minute. Okay. We're going to build that equation, dn dt is equal to r times n, and see what happens. Okay, so I'm going to just get rid of this one. Save before closing, no. And I'm going to bring over up again. And I'm going to show you that I go through a very similar process, and it's almost identical with a few interesting differences. So I go to my components. I choose my stock variable, and I can call my stock variable n, okay? I'm going to choose, I need to build the right-hand side of my equation, so I choose a flow, and I'll call this rate of change in n, okay? That's a long name. I didn't have to do that. And then I lock those up so that they look like this. And now I want to have the ndt has got two parameters, r and p. So I'm going to get a term or a parameter called r, and I'm going to get another one called p. And on the right-hand side, I'm going to construct an expression in here that involves r, p, and n. So in order to do that, I'm going to connect up with an arrow. R is going to be used, p is going to be used, and n is going to be used. And if I look in here, I can use r, p, and n. So it's going to be r times. Now, the thing you have to do is in order to type in this window, I have to move my mouse. It's a lousy thing to happen, but it's a limitation of the Java programming environment, and not that. We didn't think of trying to make it easier for you guys. Now comes one thing that's a little bit lousy in JavaScript. In most things, in most programs, if you want to take n to the power a thing, you say n and you use the carré and then you put p. That means n to the power p. But in JavaScript, you have to write something called math.power arguments n and p. So these are just things that you have to learn. It's not great, but again, it's a limitation of these programming languages. So if I want to write n to the p, I've got to write math.power n p. Now say you didn't know this, but you knew that it wasn't working. What would you do? So you go here and you would say JavaScript power constructor, maybe? Let's see what it says. Huh? Exponent, okay. Exponent expression. Exponent expression. Okay, there it is, math power. So sometimes, you know, and you can even take a, I don't recommend you do this, but if you really want to learn JavaScript, you can take an online class. But you don't have to know any JavaScript other than a couple of things like this. Okay, so now we've done that. Now when we go here, we make sure that this is a stock and not a sequence. And the initial value, let's start out with an initial value of 10. Okay? And R, let's start out with an initial value of 0.1. Okay? And P, let's start out with an initial value of 1. Okay? So what I'm going to do is I'm going to go to a model that I've already built, because we don't have much time. Let's see, discrete, continuous, population. Yeah, so here it is. I've added in this, and I've also added in a SPI. And with the SPI, I've chosen n, and what the SPI does is it tells me what the final size is going to be. And I put in the sliders, and the sliders, whatever values you want, and let's see, capture, load, exec. And now I can put it in auto mode, and then I can just change the value of p and see what happens. Wow. So now you see that when p goes greater than 1, it gets infinitely large in a finite time. So when I have other values, the final size, like when p is 0.7, the final size is 2.6. Or if I take a smaller value of r, it'll take a bigger value of p to go to infinity within 20 time units. So let's just see. Okay, 9, 1, there. So 1.2 went to infinity. Now, is this possible, that the population can become infinitely large? Well, we have an example in the textbook which looks at the world population. And I thought I had it here in this. Let me just bring it up. Let me see if I can find it here. Yeah, I don't seem to have it, but it's in your textbook. There's a graph in your textbook which shows the world population going up at a super exponential rate. So when p is greater than 1, when p is equal to 1, that equation, when you integrate it, will give you an exponential solution, e to the t. When it's greater than 1, it'll actually go to infinity in a finite time. And if you look at the world population, it can be fitted by an equation like this, very nicely, that goes to infinity in a finite time. And in fact, in your homework assignment, let's see, you'll see that if you go to figure 613 in section 6.2, you'll see the world population becoming infinitely large by 2050. So if we maintain the trajectory we're on, we're going to have an explosion of the population. Now, of course, that's not going to happen. So the question is, what are we going to do before then? And we're already starting to slow down. But for some people, the population bomb, well, in the 1970s, people talked about the population bomb, and it was like global warming now. This is the big issue. It turned out that our ability to feed the population and bring new technologies to bear was sufficient so that we could avoid that catastrophe, at least for the time being. But certainly the world population is going to have to even out. And people who predict these things can't say whether it's going to be 10 billion people, 15 billion people, what the world will look like then. But here's a take-home factoid. There are more people alive today than ever lived in the history of humankind. Good luck. Okay. So we'll see some of you tomorrow, where you'll start to work on your homework assignment and build simple NOVA models, and we'll help you with that.